Hi, in this video we are going to talk about geometric sequences. Now geometric sequences are different from the arithmetic because arithmetic was number patterns or sequences in which that from the first term to the next term we are adding or subtracting a particular number continuously and it's the same number. For example, 2 plus 2 is 4, then we have 4 is the next term, plus 2 is 6, 6 is the next term, and so forth. Here we are going to have numbers such as maybe 3 times 2 is 6, times 2 is 12, times 2 is 24. So when we see such a pattern that from the one number to the next number we are multiplying, we are going to classify it as geometric. Now let's get the formal way of writing these geometric patterns and identifying them. So number one, they will have a general solution that looks like this, that is Tn is equals to A times r to the power n minus 1. So here we need to discuss the formula and what each part of it represents. So we find that A is actually the first term of the sequence. So you just look at what is your term number 1, and then the r is found by dividing term number 2 by term number 1 and ensuring that the number that you get there is exactly equal to the number you are getting for term number 3 divided by term number 2 or term number 4 divided by term number 3. This ensures that you have a geometric common ratio. So that's how we get the common ratio, and that's how we ensure that something is geometric, or proof that something is definitely geometric, or a pattern that's given to us is actually geometric. So that's where we start off. Let's give an example. For example, we can have 2, 6, then we will have 18. So now when we look at the numbers here, T2 divided by T1 is giving us 6 divided by 2, which is exactly 3. Then when we look at T3 divided by T2, we are getting that it's becoming 18 divided by 6, which also gives us 3. So these two together means that it's geometric. So now we can find out what is the next term for this one. We would need to understand that it's going to be a multiplication by 3 onto this one. So 3 times 18, we would have that one as 54. So that would give us the exact next term. We can get more terms that follow from there, but this would be enough for us. So this is how we identify geometric patterns. Now let's look at how do we then write down the general term for this particular geometric pattern. Okay, now let's go over how to get the general term for this particular number pattern. So we've already established that we have 2, 6, 18 given to us, and then we've already talked about the fact that the common ratio, we've proven it to be 3, and we do know that our A is actually equal to term number 1, which is in this case 2. So now we can substitute into the formula and find out what our general term is. So the general term would be Tn is equals to, here we put the value of A, which is 2, then we put the value of R, n minus 1. In some cases you won't see the brackets. I just put them all the time because it helps when there are fractions or when the ratio is actually negative. But anyways, it's the safer way to go about it, that a ratio should be in brackets. It also helps to assist in knowing times when you can do laws of exponents and times that you cannot do laws of exponents, because some learners get tempted to multiply these two numbers together as a way of simplifying, in which cannot happen if they are not the same base. Alright, so anyways, what do we do with the general pattern? So the general pattern is there to help us get any term number. If I want to know term 500, for example, I would just put 500 here and it would come out. But also, what I say to students is that when you get to this point, it's time for you to check that your general pattern is actually correct by substituting any term number that's here and checking that it's actually giving you what it's supposed to. So for example, let's check for term number 3. So checking term number 3 would mean that we have 2, 3 to the power 3 minus 1. So you can check that in your calculator, but it will definitely be a 9 here. So 9 times 2 would give us 18. So that is correct. Our pattern is working. So now if you tell me any number term that I need to find, I can definitely find it. So this is what we call a geometric sequence, a pattern that is multiplicative. Now I'm going to show you that even in the division cases, we actually do it as a multiplicative pattern. Let's say that we are given the pattern 9, 3, 1. So this is the pattern that we have, and then we need to find out what is happening with this pattern. We are trying to find the general rule of this pattern. So there, when we try to check it, we would do our term number 2 divided by term number 1. In this case, it's 3 divided by 9. Don't be tempted to take the top number as the big number. You follow the rules. Term number 1, term number 2, the rule says term number 2 divided by term number 1. So the latter term divided by the former term. So in that case, we find our answer as 1 over 3. Please use the fractions, don't go to decimals, they confuse or lead to confusion. Then we have term number 3 divided by term number 2. Remember, we do this to ensure that we do have a geometric. So that gives us 1 divided by 3, but it's already equal to that. So we know that our ratio is 1 over 3. When you look at the pattern, it's actually divide by 3, divide by 3, divide by 3. But dividing by 3 and multiplying by 1 over 3 is exactly the same thing mathematically. So therefore, our general term for this one would be the first term, our A would be 9, our R is 1 over 3. So I would have here 9, 1 over 3 in brackets to the power n minus 1. So as I said previously, we do this, or I do the brackets issue to ensure that you don't get confused by the n minus 1 as if it's just for the 1, if the brackets were not there. It's n minus 1 for the entire ratio, or the exponent is for the entire ratio. So now we can even make an example by getting term number, let's say we want term number 5. So if you want to get term number 5, you would have to go in here, slot in 9, 1 over 3, 5 minus 1. So then we can go out and see that our term number 5 is going to give us 1 over 9. You can check it in your calculator, of course, to be certain that it's true. But that's definitely going to be our term number 5. So now we can get any term that they ask us for. So that's what the geometric general term does for us. Geometric general term, how to find it? You just look for the first term, find your ratio, and then use that in your general pattern. All right, let's see something now very interesting in the application of these general terms. Let's look at this example. I usually call it my COVID-19 example. Of course, not my COVID-19, but the example is mine. Anyways, I call this the COVID-19 example. Just to show you why, during COVID-19, we had our president say, please close down this country with immediate effect. That immediate effect became a very common expression, and we all went up in arms not understanding why are they closing it with immediate effect? Why are they not giving us time to get to the holidays and say that they are closing then? So let's just have an experiment that shows what happens. Of course, it's a bit of a simplified version, but definitely close to accurate. So, when we had the start of COVID-19 in South Africa, one person came to South Africa, but that scientifically we looked at the fact that when one person is infected with the virus, they usually come in contact with multiple people in the household, can usually be one or more people. Then we find that in that particular case, we need to address the fact that if the one person infects, say, 3 people, those 3 people are going to affect or infect 3 more people each. So that sends us to 9. So if each of those 3 people infect 3 more people, or each of those 9 people infect 3 more people, we get ourselves at 27 people of new infection. So one person infects 3 more people, and the more people are the new infections. So one person caused 3 people to be infected. Those 3 caused 9 people to be infected. So this gives us a geometric pattern if we look at it, because the ratio will be 3, and then our A is 1. So we have Tn equals to 1. We don't need to write the 1. I'll just keep it there. It's fine. Now, please look at what happens if we look at what would happen after 15 days. Say that this is day 1, 2, 3, 4. After 15 days, we have ourselves this particular number here. So you can put it in the calculator, but what it gives us is that we would have 782,969 new cases. That's what Ramaphosa was shown. Mr. Cyril Ramaphosa, that is our beloved president. That's what he was shown. Now, Imagine you being the president and you get to be shown this, that after day 15, you can even try day 16 and 17, see how shocking it gets. After 15 days, the new cases in the country would be 4,782,969. That is a huge portion of the population. So that is why he had no other choice, guys. He had to close the country down with immediate effect as soon as possible to save lives. So this is what we have, applications of geometric series. Next time we'll talk about the sum, which is when we had the graphs that they showed us was new cases, and then they showed us what was the total number of people infected since day 1. So that's the series part of it. That's the one that is going to follow next. Now let's look at the geometric series. So the geometric series means geometric sum. So we are adding all the terms of the geometric pattern onto themselves so that we get the total since the beginning. That's what series does, or that's what summation does. So the definition, remember, of summation or series is, if you want Sn, you are going to add term number 1 to term number 2, term number 2 to term number 3, and then go on until you get to term number n, which is whatever last n number that they put for you here. So if it's S5, let's say, you take term number 1 plus term number 2 plus term number 3 plus term number 4 plus term number 5, then you can get for those 5 terms what is the total. So it's a concept that has a huge application in finance and other places, also in the disease spread that we looked at in the sequences side for the COVID-19 cases. So we have 2 types of series formulas that we are going to use. The first one is, if it happens that we are dealing with the sequence that has r greater than 1, we are going to use this formula here, which says that take your your first term again, then you have your ratio to the power n minus 1 divided by r minus 1. Then the proof of these things we can do in another video. There's no need to do them here, but I'll have the proofs ready for you in another video that you can take a look at. Or the derivation, how these formulas come about. We can do a video for you, or we will do a video for you just to see them, to have better understanding of how did we even get here. But for now, it's a formula that's given in the formula sheet. You just need to know how to use it. Then we have this case that if r is less than 1, so either a fraction less than 1 or it's a negative number, we are going to use this formula here where the 1 and the r are swapped around. So this is going to be able to add all the terms for us. Then we can get the series of that particular geometric pattern that we are working with. Let's look at an example of a geometric series and how we go about solving it. So let's say we are asked to find S5. So that's the sum of the first 5 terms of the sequence that is given as 1, 2, 4. So before you do any summation, you first have to check what type of sequence you have. Remember, now we're doing arithmetic, geometric separately, but in the examination, you're usually not told which sequence you have. You have to first check. So if we check here to here, it's a times 2. Here to here, it's a times 2, or we can do that t2 divided by t1 is equals to 2 over 1, but that's the same as 4 divided by 2, so the answer would be 2. So yes, it is definitely geometric. Now, we know our a is 1 and our ratio is 2. So because our ratio is greater than 1, we are going to use the formula Sn is equals to a rn minus 1 r minus 1. So we use this formula. Now let's check. This formula is going to tell us that for us to get S5, we need to put 1 here as our first term. Then here we're going to put 2 to the power n. Again, so the n we know is 5. Again, I usually say that get used to putting this one in its own brackets. Then minus 1 and then divide by 2 minus 1. Plug it into the calculator, you are going to see that it's going to give you 31 as the sum of the first 5 terms. This is actually sum of 2, 4, 8 would be the next one, 16 would be the next one. You can even do it manually to check that what the formula did for you is exactly what we're supposed to have. But remember, we are learning formulas because sometimes they'll ask you for S50, S500, S5 billion. How would you do that manually? We have the whole day, you take the whole day and still not find it. So it's better to have a formula that does everything for us. We will see that issue that we can predict some of them using the infinite sum, but others you can't even predict. You need to do it using the formula in order to save time and for accuracy. So this is how we find the geometric series. Again, for the geometric series and sequence, both of them, You need your first term and you need your ratio. Once you get those two, you're done. Plug it into the formulas do the job for you.